All right, let's talk about arc length and curvature. And for the most part, arc length is not like a crazy new concept, right? In Calc BC, you recall that arc length for like a parametric function ended up being the integral from some time a to a time b of square root dx dt squared plus dy dt squared dt, right? You were integrating with respect to time. And you can prove that, like, or not. I don't think it's a very rigorous proof, but you can manipulate and you can actually figure out if you use Pythagorean theorem. That formula does indeed hold. For the 3D world, you just got to add in that dz dt squared component, right? So it's not like a crazy addition. And now that we're working with now that we're working with vectors, this whole little quantity right here, right? We're taking, right? If dx dt, if we had a function, if we had like a function that was sort of like, if you had a function that was like r of t equals like f prime of t g or g of t, sorry, f of t, g of t, h of t, then these just end up being the derivatives of those components. So this square root, dx squared or dx dt squared, dy dt squared, dz dt squared term, this just ends up being the magnitude of the derivative of our vector function. And when we're dealing with position, all right, if position is r of t, then this derivative is velocity, right? V of t, or not V of t, but it's r prime of t. And when you take that magnitude, right, this right here, this is the arc length function, right? This gives us like the total distance traveled. Not really I guess this is the total distance, right? This gives us the distance traveled at a time t. And I should change this. This is really, we need to have different variables. It should more be r of u, or like r of u du, r prime of u du. And this, if you remember from physics, right, this is very similar to our distance, distance formula, right? Distance is equal to velocity times time, and really, or speed times time, and really to do it, you have to integrate velocity or speed dt to get the total distance if your speed is changing. So these aren't really like newish ideas. This is just applying what we've already learned about vectors and kind of what we've learned in Calc 2 or Calc BC. So the next big idea is, and also for the arc length function, obviously note these have to be continuous functions, right? You can't really find the arc length of functions with holes or discontinuities. And also, let me just check my book. For this function, I believe the case is that this kind of function really only works if C, where C is like our curve, right, it only travels like in one direction, like it's only traveled once. Because if you had, I guess, maybe like a alternating function, or like an oscillating, I guess, function where your vector is kind of moving in a circle, I guess this distance wouldn't really work. Or would it? No, I guess it wouldn't. I have to think more about that. But in most cases, like you'll see, like for a function like this, we can use the arc length function. So curvature, let's talk about curvature. So really, curvature is defined as, there's these two equations up here, but I want to make sense of them. Curvature is really defined as, I'm going to use this space over here. These are examples, but I'm going to erase it once I'm done. So we'll go on these examples in a second. But curvature is really, I want to go over the content first and then we can do examples. Curvature is really the absolute, or the magnitude, of the change in the tangent vector function. So hopefully you remember tangent vector functions, right? The tangent vector to a curve is really just the derivative of the position vector divided by the magnitude of the derivative. That's how you make it a unit vector. It's a unit tangent vector. So it's really the change in this vector, not with respect to time, but with respect to length, which is kind of weird. But if you think about a curve, right? Let me draw a curve right here, right, in space. You can imagine that for this very small change in length, ds, right? This is what we call ds. The tangent vector doesn't really change much, right? It is still, it changes, but doesn't change a whole very drastically. Take a look at this ds right here, right? The tangent vector is like this here for this ds, and then the tangent vector changes like that by the end of the, or by this, by this point, right? So for this ds, this very small change in length, the tangent vector changes a lot more here. So we say it has more curvature because the change in tangent vector with respect to the change in length is larger. So hopefully that kind of makes sense, right? How can you now it's weird to take derivatives with respect to length, right? Our functions are parameterized with respect to time. So you could, the book does have a way you could like reparameterize it or whatever. That's just silly. We don't really need to do that. What we can do instead is say, hey, well, I know this will just really equal the magnitude of dt, or d, this is gonna be weird, d of dt of the tangent vector, so the time derivative of the tangent vector times, well, to get a ds on the bottom, we have to multiply by dt ds. Well, hey, let's actually go over here, right? If this is s, our kind of distance, right, or the displacement, or yeah, I guess distance, or the arc length along that function, well, if you take the time derivative, I guess I should do this. If I take the time derivative, right, on both sides, by the fundamental theorem of calculus, I get that s of t, or ds dt, is really equal to the magnitude of the velocity vector, right? So I guess ds dt, I guess it's really like this with the t variable when you do your FCC. And then, right, ds dt is really just the change, or is really just the magnitude of the velocity vector, which makes sense, right? The change in length over change in time just ends up being the speed, or the magnitude of the velocity vector. So what I really get is this is kind of weird. I guess the absolute value signs make it kind of weird, but I really get the derivative of the tangent vector over, because I'm getting the reciprocal of ds dt over r prime of t. So this is our first form. Now, I'm not really going to derive the second form, mainly because it's just like, I don't think it's really necessary to, but if you are interested, please let me know. I can do it. I just think for most people maybe watching this, they're not as so interested. But if you don't want to find the tangent vector, is there really a bit more of a quick way to do it is if you, or I guess not quick, but if you're given the position vector, you could just take the first derivative and the second derivative, take the cross product, take its magnitude, divide it by the magnitude of the velocity vector. So that is how another way you can really go about doing it. And then the normal vector. So if you have a curve, I guess I shouldn't have erased the curve, would be a good representation. If you have a curve in 3D, you can actually find a lot of vectors that are normal or perpendicular, right? Normal is just another word for perpendicular. There's a lot of vectors that can be perpendicular to a curve at any point, right? Really, I can even put a plane that is kind of normal to the curve, and then every vector that lies on that plane would end up being normal. But a nice helpful definition of the normal vector is if you use the derivative of the time, the derivative of the tangent vector. So what you can actually do, and let me actually show this to you, is if let's say you have your tangent vector, okay? Just your good old tangent vector. And let's say we take the dot product of the tangent vector. Well, when you take a dot product with a vector itself, you get some sort of value, right? Because what you really get is you get in this case, you get 1, right? So you would get 1. You would get 1 because the tangent vector has a magnitude 1, and the dot product is always going to equal the magnitude of the first vector times the magnitude of the second vector times cosine theta, the angle in between. Angle in between a vector of itself is just 0, right? The vector, they both, like, they'll point in the same direction as itself. The angle is 0, so cosine 0 just becomes 1. And now you have magnitude of the tangent vector times the magnitude of the tangent vector. Tangent vector is a unit vector, so it just ends up being 1. So this is actually equal to 1. And so when you were to if you were to take the derivative with respect to both sides, you get the derivative is going to be 0, right? Derivative of 1 is equal to 0. Well, now what I see is that, okay, let's just use the product rule for dot products, right? We could say that, hey, it's going to be tangent t times the derivative of t times t plus, or am I doing this right? Oh, yeah, I think I am. I'll check the book in a second. But I basically get this. Right? If I do my product rule, right, I'm always doing f prime g, f g prime. But because it's like the same tangent function, I really get t prime of t dot t of t plus t prime of t dot t of t. Or I guess I can even do it like t of t times t prime of t, right, to make that distinction. So I really get 2 times t prime of t dot t of t is equal to 0. And, you know, from this, I guess you could, this is the same. So 2 times t prime of t dot t of t, this is the same as this. You can actually prove that. I believe so. I think that's one of the properties. If that's not, please correct me. Pretty confident it's one of the properties, because if you were to take a dot product, it's like you're doing 2 times each of these components, and then those components get multiplied with that. So that would be the same thing as just multiplying the components first and then tacking on a 2. So you can actually do that. I don't want to spread misinformation. I just don't have the properties memorized. But this property just kind of makes intuitive sense, which is good, right? We don't want to memorize. We'd rather want to understand. Let me look at the dot product properties. Oh, where are they? Look, you're supposed to give me them. What the heck? Where are... Yeah, that's a valid property. Okay, divide both sides by 2. I get t prime of t dot t of t equals 0. What this tells us is that the derivative of the tangent vector will actually be perpendicular to the tangent vector itself, because they're both dotted like so. And what you'd find is that on your curve, if you were to take your curve, right, if this is a section of my curve, if my tangent vector is this way, and my new tangent vector is this way, right, at the tangent at that time, so time A, time B, then the t prime of t, the change in tangent vector, would have to point, obviously orthogonal, but it wouldn't point perpendicular out of the page or into the page. It would kind of point, I guess, in the direction that's curving, right? Because it's going to try to change that vector, right? Because if you take like over really small time intervals, if you do your vector addition, I would get something like this. And you could see that's kind of roughly equal to the tangent vector over here, right? Because it's trying to add. So, wait, that doesn't make much sense. Let me explain that further. The idea is that, well, over really small time intervals, to get a tangent vector to go from here to kind of like this, you need to have a derivative, or the derivative kind of like that, because the derivative is just like, if you think about, this is hard to explain. Because if you have small time intervals, right, over small time intervals, really, your total change, so your total change in the tangent vector is really just going to equal dt times the change in time. So as, you know, obviously as change in t approaches 0. But the idea being, I guess you don't even have to go that far. You don't have to take any limits. But the idea being the change in tangent that I'm adding to this tangent vector is equal to the time derivative times the really small time interval. Huh. I have to think about it more. But the idea being the change in the derivative of the tangent vector would point towards a curvature. Now, that's obviously normal to the tangent vector, and that's a really helpful way to get a normal vector that would be a unit vector. It's just a derivative of the tangent vector over t prime of t. And the binormal vector is going to be the tangent vector cross the normal vector. So if I were to draw it using a curve, then we have my tangent vector here, my normal vector here. So if these are making a right angle, t cross n, my binormal vector, would kind of point perpendicular to both this way. So that's just another, I guess, helpful kind of definition to know. Enough of that. Let me honestly just go over the examples, right? I'm sure you're done with me talking. Let me go over two examples that involve both arc length and curvature. So, for the length of a curve, we want to find the length of this curve right here from 0 to 1. So, I know that let's just really, right, we know that really the arc length is going to be the integral from 0 to 1, right? L is going to equal to the integral from 0 to 1, r prime of t, the magnitude of r prime of t dt. So, let's find r prime of t, or let's find r prime of t. So, r prime of t, taking the derivative, right? So I get 2t for the y component, and then t squared for the z component. And then the magnitude of that, so if I take the magnitude of r prime of t, is going to equal square root 2 squared plus 2t squared plus t squared squared. Woo! Okay, so this simplifies to 4 plus 4t squared plus t to the 4th. Now, if I were to just integrate this by myself, it would be a pain in the butt, and I don't actually know if there probably is a solution for this integral. Well, there is a solution for this integral because, you could simplify this. What you could say is, well, hey, if I think of this as 4 plus 4t squared to the 1 power plus t squared to the 2nd power, this is really equivalent. This is actually just a binomial. This is just a binomial where instead of x, it's like x squared. You know what I mean? Because now my variable is being squared, so it's t squared to the 1 and then t squared to the 2. It's really kind of like a binomial. So I guess it's not actually a binomial because it's t to the 4th, but I can factor it out like one. And I believe this actually is a perfect square because I get t squared plus 2, I believe, squared, right? Because if I FOIL this out, yeah, I would get t to the 4th, and then this times that would be 4t squared, because I multiply twice, and then I get 4. Awesome. So then this is really just the square root cancel out the square, and then I get t squared plus 2. So I'm really integrating. L is really going to be from 0 to 1, t squared plus 2 dt. So this is the same thing as 1/3 t squared plus 2t from 0 to 1. I get 1/3 plus 2, which is going to equal 7/3. When I substitute in the 1, and I don't really have to worry about the 0 because 0 time when I do my zeros, my the minus when I have to do this plugged in 1 minus this plugged in 0. When I plug in 0, it all just becomes 0. So I just got to plug in 1 and I get 7/3. So that was how you could really, once again, really quick way to just find the length of the curve. You're just taking that integral. So let's do this one. We're going to find t of t and n of t for r prime of t. And then just because I forgot to, let's just also find the curvature. Also find k. So, or kappa, I think it's a Greek letter, right, if you read the book. So let's do this. So we know tangent vector is really just r prime of t divided by its magnitude. That's how you get the unit vector that is tangent to the curve. So let's find r prime of t. So r prime of t is going to equal, so root 2 tt, oh my god, this is a tongue twister. Root 2 times t, the derivative of that is just root 2. Then e to the t, its derivative is just e to the t. And then e to the negative t, right, you have to do chain rules, because you're going to take the derivative of the inner, which is just e to the negative t, times the derivative, or derivative of like the outer, which is e to the negative t. And then you take the derivative of the, multiply by the derivative of the inner, which is negative 1. That's chain rule for you. So I really get, this is really going to equal negative e to the negative t. Okay, so now I want to find the magnitude of r of t, r prime of t. So if I find the magnitude, r prime of t, so I get square root 2 squared plus e to the t squared plus e to the negative t squared. Now, the deal is well, you know, obviously the square root cancels out, and then this is just e to the 2t, right? Exponent properties. E to the t squared is just the same as e to the 2t. Same thing here. Oh, I forgot the minus. It should be minus negative e to the negative t, but it's a square, so it wouldn't have mattered, right? The square kind of cancels that out. Or not cancels it out, but I guess, yeah, it cancels it out because you're multiplying by negative 1. So then I get e to the negative 2t. Now, once again, if I leave it like this, I'm obviously, well, I guess, to find the normal vector, I know I'm going to have to take the derivative. So if I just take this magnitude and divide it by, take this vector and divide it by this magnitude, when I'm going to have to go take the derivative to find the normal vector, that's going to be really nasty. I just don't want to do that. What I can do, or you can, but it's going to be pretty bad. You could do it though. But what I can do is I can actually factor out an e to the 2t. This is not, honestly, this is not a very, I guess, intuitive thing to think of. But because I know that I have a 2t term and another kind of negative 2t term and no e to the 2t term there, you can kind of manipulate this, right? In the same way that if you had 1 plus x squared plus x to the negative 2, right? You can actually factor out an x squared and get x to the negative 2, right? Because when I factor out an x squared from 1, I get x to the negative 2. When I multiply it back, I just go back to 1 plus x to the negative 4. And then you could see how we can do the same binomial trick that we did last time. So we can actually just do the same thing for e to the 2t. So e to the 2t, so I get 2 e to the negative 2t plus 1 plus e to the negative 4t. And remember, when I distribute back the e to the 2t, I get the same thing. Well, now, first of all, I could just pull the e to the 2t out because the square root of e to the 2t would just be e to the t power. Now, I have this e to the negative 4t term. Well, that's the same as e to the negative 2t squared plus 2 e to the negative 2t, and that's like a first order term. And then there's no term for the last term. This is taking a binomial form. So I can factor it out, or not, I guess not factor. What's the word when you have a squared out binomial and then you go backwards? I don't know, but you can, this is really the same thing as 8 e to the negative 2t plus 1 squared, right? When I square this out, I get the same thing up here. So I can cancel this out right here. So I get the square root, cancel out the square. So I get e to the t times e to the negative 2t plus 1. And then I get, now I get e to the negative t plus e to the t, which is just a nicer to work with. You're going to see in a second. So now, so I know t of t, the tangent vector, is going to equal this divided by the magnitude, right? So I have root 2 over e to the t plus e to the negative t. I have e to the t over e to the t plus e to the negative t. Then I have negative e to the negative t over e to the t plus e to the negative t. Now I can find, oh boy, the second derivative, the derivative of this, which is gonna be a little bit nasty. I don't think I expected it to be this nasty. So I'm actually gonna erase this. Yeah, I'll erase it just so I have some more space. And then I'll just keep this right here. And then what I can do is this is kind of bad to follow, but we'll just do it because I don't have all the space in the world. Now, when I'm taking the derivative of this, I'm going to say t prime of t prime of t is going to equal, okay, let's do this. The root 2 we don't have to worry about. So we can actually just, we don't really have to worry about the root 2. Actually, never mind, let's just do it like this. So we have the root 2, and I'm really doing this stuff to the negative 1. So e to the t plus e to the negative t. Okay, so to the negative 1. I'll do it one at a time, one component at a time. So I'll do my reverse power rules, or my power rule, sorry. Negative 1 over, or negative 1 times this stuff, and then to the negative 2, right, when I do my power rule. So I pull out the negative 1 in the front, and then I subtract 1, I get negative 2. And then I take the derivative of the inner. So I get e to the t plus e to the, so e to the t is that derivative, and minus e to the t here. Right, it's minus e to the negative t. Okay, so that's 1. Now for the second component, I have to do I have to do quotient rule? Maybe I could factor it out actually. I haven't done this problem. I'm kind of winging it. So for this, I could do e to the t. I could factor out, I'm doing really the derivative of this stuff. But what I could do is I could factor out e to the t here, and then I get 1 plus e to the negative 2t. That's actually a bit nicer to work with. That's actually way nicer to work with. So I can actually cancel out. I just get 1. So really, I'm taking the derivative of 1 times, or I'm really taking the derivative of 1 plus e to the negative 2t to the negative 1. So I'm doing the same thing, right? I do my reverse, or I do my power rule, and I multiply by the derivative of the inside. So I get, I'm going to get, let's do, so derivative of the inner is just negative 2. So the negatives will actually drop there. 2 times e to the negative 2t. Wow, okay. So then, I'm going to do the last component. I can do the same trick. I can actually factor out, I guess it's a little bit different here because it's a negative. Well, no worries. I can just pull the negative out in front here. And then I should get negative, this is really taking the derivative of negative 1 over 1 plus e to the 2t, I believe. Right? To the negative 1. Right? I'll check the solution at the end. But I'm going to just quickly get rid of that. I'm going to do my reverse power rule, so to the negative 2 times 2e to the 2t. Okay. Oh my god. Now, this is kind of crazy. I'm going to get root 2. I'm going to get, oh my god, e to the t minus e to the negative t of e to the t plus e to the negative t. And then I get 1 over 1 plus e to the negative 2t. Or I get 2, that's so weird. I get 2 e to the negative 2t over this stuff. And then I get 2 e to the 2t over 1 plus e to the 1 plus e to the 2t squared. That's the tangent vector, I think. Now you could take the derivative from, or no, this is the derivative of the tangent vector. To find the normal vector, I just take the magnitude of this, which I really don't. You have to take the magnitude of this and then divide it by this stuff, which I might not do. I know what is. I'm not gonna do it just because I know it's gonna take a little bit of time. And honestly, I don't know if I'm doing this right. So maybe I'll post a solution, or I'll post a solution. But yeah, this is kind of a crazy problem. To find kappa though, we already got t prime of t. We would once again take its magnitude and then divide it by the magnitude of. You would divide it by the magnitude of r prime of t, which is really just right magnitude of r prime of t. You just divide. It's just e to the t plus e to the negative t. So yeah, kind of a crazy problem, but I'd say we got through 70% of it. Last step is just find the magnitude. So I just dropped my marker. Thank you for watching this. I know this is kind of a crazy. I dropped my marker again, but I'm not even gonna sweat it. Yeah, this is kind of a crazy video. But yeah, thank you for watching.